Problem 6 here, and in part A, what we need to do is show that the first 4 non-zero terms of the Maclaurin series for f are these 4 terms, yeah? So first, let's remind ourselves of what a Maclaurin series is. Remember, a Maclaurin series is an infinite sum that equals exactly functions f of x when it exists, right? And so like the function f of x will equal the infinite sum n equals 0 to infinity of fn of 0 divided by n factorial and then times x minus 0 to the nth power. So it's a Taylor series centered at 0, as we already know, or as we should already know. And x minus 0 to the nth I could just write as x to the nth, so I'll write that. All right, cool. Now, if we write these in expanded form so that we can see, like, you know, term by term what they look like, then first is n equals 0, right? We plug in n equals 0. So this n here, crucial that you understand what this n means. This n here means nth derivative of f. So when n is equal to 0, it means the 0th derivative of f, evaluated as 0, of course. But the 0th derivative of f is like before we took any derivatives of f, so that's the function f evaluated at 0. That's what this will mean when n is 0. It means f of 0. Yeah? Okay, and then we have f of 0 divided by 0 factorial. 0 factorial, remember, is 1. And then x to the 0 is 1. So we just have f of 0 as our very first term. So we have f of 0 plus, and then when n is 1, this will say f1 of 0. That means f prime of 0, the first derivative. So the numerator is f prime of 0, or the first derivative at 0. So f prime of 0. And then the denominator is 1 factorial when n is 1, and this is x to the first. So I won't divide by 1, but I'll write x to the first as simply x. So we have times x, right? And then next we have that the third term will be, more generally that is, it will be f2, which again means the second derivative, evaluated at 0, and then divided by 2 factorial, and then x to the second. And then plus f3, the third derivative, evaluated at 0, divided by 3 factorial, and then x to the third. And then f4, the fourth derivative, evaluated at 0, divided by 4 factorial, and then x to the fourth, right? And then on and on and on. It's an infinite sum. Hopefully not more than one of these is 0. That way we still get 4 terms. Let's see. Let's try our luck. So first, we know that this is equal to 0 by that. So f of x starts with f of 0 being 0 because of that. So we have 0 plus, but why bother even writing that 0, right? Okay, so we'll just skip it, and then we'll go to this. Now, f prime of 0 is given to be 1, so we just have 1 times x, which is just x. Nice. Okay, so this and this so far match. What's next? Well, hopefully a negative term. So we go plus, and then this here, what is that? Well, for n more than 1, we're given a formula here that's recursively defined so that we could use this formula to find the second derivative, the third derivative, and the fourth derivative, and so on. So I'll do this part in black. And so when we find f2, the second derivative, at 0, the formula says that we should first write f of something plus 1, right? Well, if we want 2, it's got to be 1 plus 1. So we're saying n has to be 1 in this particular case. And then we have f 0. Now, this here exactly matches that form. So looking on the right side, which is right here, we see that what we have to write is negative 1, since n is 1, and then times f1, which is f prime, of 0, right? Okay, cool. So this is saying negative 1 times f prime of 0. We already had f prime of 0, so that's going to be negative 1. Yeah? Okay, cool. So we just said, I'll summarize this. We just said that f2, the second derivative at 0 of our function f, is equal to negative 1. That's what we just discovered, right? That equals negative 1. Okay, cool. So we have that this is -1, and then we know that 2 factorial is 2. So this next term is going to be -1 divided by 2, right? And then times x squared. But wait, plus and then a negative number is cumbersome. We could just write minus and then, oh, sorry, I'm deleting elsewhere, aren't I? Yeah, so we could, what I'm saying is get rid of this and write minus 1/2 x squared. But why do that? We could just write minus x squared over 2. So that way we are even more like what they want, right? Okay, cool. And so then this here has given us a clue as to how we should find that, right? So that then is going to be f3 of 0, mimicking our steps for the second derivative at 0. We see that we have to write f2 plus 1. That parenthesis was too big. 2 plus 1 of 0. So this time n is 2. So we'll have that that's -2. I'm looking here. And then times f2, the second derivative at 0. So that's going to say -2 times the second derivative at 0 we said was -1. So it's -2 times -1. And so that's going to be 2. So we just learned that the third derivative at 0 is going to be equal to 2, right? Okay, cool. All right, next is the fourth derivative, and that's the last one we'll need, right? Well, yeah, so based on the pattern so far, the fourth derivative at 0 should be equal to, we know that this is going to be -1 less than this, so -3, right, times, and then it's going to be, well, I don't need a parenthesis, and it's going to be times the third derivative at 0. So that's, that 0 is ugly. Okay, at 0. So this is going to say -3 times, and this here is 2. So -3 times 2, or -6. Yeah, so that's the third derivative, the fourth derivative, -6, right? The fourth derivative at 0 is -6, right? Okay, cool. So we've got everything we need now. So then continuing on where we left off here, we'd already taken care of that. So moving on to this, we see that this part is going to be 2, and then we know that 3 factorial is 6. So 2 divided by 6 is going to be a third times x cubed. We could just write that as x cubed divided by 3, right? Okay, and then plus the fourth term, the last one that we'll have to find to match that, will have to be this, which is -6. We all know 4 factorial is 24, so it's actually not plus, it's going to be -6 over 24, and then x to the 4th, right? Okay, but we could reduce that as just saying this is just a quarter, so it's just -x to the 4th over 4. And based on the pattern that we clearly see from these first 4 non-zero terms, we know that if we were to continue, the nth term, which is the general term, would have to be, it's -1 to some power, right? And because they're alternating, it's positive, negative. So it's -1 to some power if you want to alternate. And then we'll figure out what that exponent on -1 has to be shortly. But then otherwise, we know that it's going to be x to the n divided by n, right? Now, what do we want? We want, in front of the even terms, we want a -1. And in front of the odd terms, we want a +1. So like we want to say -1 to the n plus 1 power, right? Because that way, like when n is 1, we see that we're going to get -1 squared, so it will be positive. But when n is 2, it's going to be 2 plus 1, and so -1 to the third, and so negative, and so on. Yeah, you see that? You see that? Okay, cool. So this should do the trick, and this should be everything for part A. Keep watching. All right. Part B here, and in this part, we have to determine if the series we found in part A, which is this, converges absolutely, or if it converges conditionally, or if it diverges when x is equal to 1. Now, when x is equal to 1, this series turns into the series in black. And so what we have to do is determine if this series in black converges absolutely, converges conditionally, or diverges, right? Okay, now, to determine which of the three applies to this series, I remind you that the harmonic series, right? The harmonic series, that's a harmonic series, right? The harmonic series diverges somehow, and I will make a video about the harmonic series and why it diverges. But we also know that the alternating harmonic series, right? The alternating harmonic series converges, right? So they're very similar looking series. One of them alternates while the other doesn't. And the one that doesn't, the harmonic series, diverges, whereas the alternating harmonic series converges. Okay, and therefore, when I put absolute values around here, which is what I need to do to determine absolute convergence, I will note that I will lose the alternating aspect of this series, and therefore I will get a series like the harmonic series, which I know diverges. Whereas if I don't have those absolute values, then this series is like the alternating harmonic series, so it converges. So our answer is that it does not absolutely converge. It converges conditionally. So here it is. Converges conditionally. And you could like kind of summarize what I just said as like your corroboration. Yeah? Okay. Okay, cool. All right, keep watching part C and D to come. Part C here, and what we have to do in this part is find the first four non-zero terms and the general term for the Maclaurin series of the function g, where g is defined as the integral from 0 to x of f of t dt. Now focus on this because f of t is the same function as f of x, which we found to equal this, except instead of x here and x there, we'll use a t. Right? That's what f of t is. Yeah? Okay, cool. Now, if we write f of t so that, you know, we see the first four non-zero terms, then f of t will have to be t minus t squared over 2, and then plus t cubed divided by 3, and then minus t to the fourth divided by 4, and then plus dot, and then plus the general term was like -1 to the n plus 1. We already have the general form right there, except instead of an x we use a t. But yeah, t to the n divided by n, right? Okay, and then plus dot, right? This is what f of t would equal. Since g of x is the integral from 0 to x of f of t, then g of x, we'd say, is equal to the integral from, I'm squeezing that in, from 0 to x, and then a dt right there, my bad. And so then we just write a 0 to x right here, and then a dt right there, and we can find g of x more generally, and therefore we can identify the first four non-zero terms and the general term for g of x. Okay, so g of x then is going to equal, we can find these antiderivatives term by term, and so doing that we can write that it's going to equal t squared divided by 2, right? And that's the antiderivative of that, and then for this we'll have minus, and then it'll be t cubed divided by 6, but I'm going to choose to write 2 times 3 instead of 6, and then it'll be plus t to the fourth divided by, and then it's going to be divided by 12, but again I'm going to write 3 times 4. It'll be revealing to write it in this fashion when we get to the general term, that is. And so minus t to the fifth divided by, and then it's going to be 4 times 5, right? 4 times 5, and then plus dot, and then it's going to be -1 to the n plus 1, and then clearly t to the n plus 1 divided by n times n plus 1, right? Okay, right? I don't like that n in the denominator, so n times n plus 1, right? Okay, cool. And then plus dot dot dot, and of course we need to evaluate this at 0 and then at x. Well, actually backwards, at x and then at 0. So evaluate at x and at 0 and take the difference. Notice when we plug in 0, all of them are gonna turn to 0, right? All of them. And when we plug in x, all that'll happen is all the t's turn into x. This will turn into an x, that, and then this, right? Okay, so basically what I'm saying is like, I'm gonna save myself some writing, but yeah, like you just replace all the t's with an x, and from that you've got the first 4 non-zero terms of g, and then the general term. And clearly the way it's written right now, g of x doesn't make sense because these guys are in terms of t, but we just explained how you need to replace all of these t's with an x. Yeah, okay, cool. Part D and the final part to come, and that's it. Keep watching.